Hello students, welcome to this lecture in which we're going to talk about fundamental theorem of line integrals. And the theorem says that suppose that our path is given in vector form and our t is between little c and little d, and this is uppercase C. Then couple of conditions on the c and some function f. We're gonna suppose that c is piecewise smooth. And what do we mean by piecewise smooth? That means that it's differentiable, except maybe at some points, we put it in, except perhaps at finitely many points. And finitely many means you can count them, finitely many points. Also, some conditions on function f. Suppose that function f is continuously differentiable, and probably you haven't heard about this term, so let's put a small description about it. So what is continuously differentiable? That means it's differentiable function, and it's differentiable everywhere, and derivative is continuous also. So, and derivative, if you calculate it, it's going to be a continuous function, and derivative is continuous itself. And that's what it means, continuously differentiable. Where is it continuously differentiable? It's continuously differentiable on an open set that contains S, as I said, that contains C. All right, so we have our prerequisites for the theorem. What does the theorem say? The theorem says that if you take integral along this path of the gradient of f dot dr, which is going to be a vector, you're going to get the f of b minus f of a, where b is equal to v evaluated at d, and a is equal to v evaluated at c, where d and c are the endpoints of the interval for the parameter t. So that's our theorem. Let's try to prove it to see how it works. So what would be the proof for this theorem? So let's first of all write our v of t. V of t is given by function for x, function for y, and function for z. And it's a vector function. And t is changing between c and d. So what are the functions here? X of t, y of t, and z of t are piecewise smooth. piecewise smooth on this interval from C to D. All right, now we calculate the derivative of V. So derivative of V is going to be x prime, y prime, and z prime, and this derivative exists because we have our smooth functions. So we have to recall what is the gradient of f is. The gradient of f is partial with respect to x, partial with respect to y, and partial with respect to z, put together in one vector. So now we're going to construct some things. So consider line integral of the gradient of f that this should be dv, sorry. Should be dv here. I wrote dr, that's the wrong thing. This should be dv. Alright, so consider our dot product inside of the integral. So we have an integral from C to D, and we have fx, fy, and fz dot x prime of t, y prime of t, and z prime of t. And here we have dt, z prime of t, dt. Okay, so let's calculate the dot product. We have integral from C to D. So it's going to be f partial with respect to x times x prime of t plus partial with respect to y times y prime of t plus partial with respect to z times z prime of t dt. Right, so let's think of it as formula star. So now we need to use a chain rule. So recall the chain rule. The chain rule, what does it say? It says if f is equal to function of x, y, and z, then if you want to calculate derivative of f with respect to time, you have to take f prime of x of t, y of t, z of t, and construct a dot product with x prime of t, y prime of t, and z prime of t. All right, so which is exactly the things that we have. Y prime of t and partial with respect to z times z prime of t. Right, and this will be f prime of t. This will be f prime of t. So how does it help us? It helps us to say that if we go back to star becomes, if we use this idea, star becomes integral from C to D of f prime of t dt. All right, but this is just our Calc 1 idea, so this is just f of v of a minus, this is obviously, this is d. And here we have f of v of c, or f of b minus f of a like in old days, right? Like in the old days. So conclusion, if we want to calculate the integral, line integral of the gradient of f dot dv, is going to be f of v minus f of a. So we're done with this theorem. We proved it. So how does it help us? Let's go and use this idea a little bit for the examples, but before that we need to go through some mathematical ideas first. So recall that if the function f is equal to the gradient of little f, then f is a conservative vector field, is a conservative vector field. Now, next thing to remember, that's a little bit of physics here. So we're going to talk about work. So work done is a scalar, and it's defined as as follows: work equal force applied to a particle times displacement. So if force is constant, then you just multiply force by displacement like you do in a regular physics class. That's very simple. The problem starts when the force is not really constant. So the calculation gets interesting. If the force, or if a force, we don't know which force, so if a force is not constant, So also we have to add is to exerted parallel to the displacement. I didn't spell it right. Parallel to the displacement. So if the force is not parallel to the displacement, then we're in trouble. It's not that easy to calculate. So we can derive force as follows. For the general case, for the hard case, we can define work as follows. Let me give a name, work W, as follows. We'll say that W is equal to, it's usually lowercase w, W is equal to the line integral of f dot dv. So in our case, we can think of it as integral from a to b f dot v prime of t dt, where C has been parameterized. All right, so if we parameterize C, then we can put an equality sign here and get it in terms of A to B, and we have dt at the end. Here we have V prime of t. All right, so next theorem we can put as the following. The theorem says that the work that is done moving a particle through a conservative vector field is independent of the path. Independent of the path. We're not going to prove this theorem, but it could be done, it could be proven. So finally we can look at the example for all of these ideas. So let's look at this example. Suppose we have a vector field which is negative x over x squared plus y squared plus z squared to the 3/2, negative y divided by x squared plus y squared plus z squared to the 3/2, and the last one is negative z divided by x squared plus y squared plus z squared raised to the 3/2. And we have the angled bracket for our vector. Now we're gonna suppose that a particle travels through this vector field along a path and the path is given by v of t equal to 1 plus t 2t cubed minus 1 t squared cosine of pi t for t between 0 and 1. Okay, so the question, find work done by moving a particle right, so we have to find the work that is done by moving a particle. So how we're going to do that? We need to set up the integral, right? So in principle, principle, we could set up and evaluate the integral. Set up and evaluate the integral. Right, so let's try. So we have to recall a couple of things. So we need the force that is equal to the gradient of 1 over x squared plus y squared plus z squared to the 1/2, right? Okay. So then we use fundamental theorem of path integrals. So fundamental theorem of path integrals applies so we have so why do I get this? Because if I take derivative of 1 of the square root, I get exactly this expression over here, right? So we have a path integral or line integral f dot dv equal to the line integral of gradient of f dot dv, which in our case is it's going to be 1 over, so we use this function over here, x squared plus y squared plus z squared to the 1/2, evaluated from the first point over here, 1, -1, and 0. How do we get this? We plug in t equals to 0 into this expression, so t will be 0, so it's going to be 1, going to be -1, and cosine of 0 is also 1 times 0, so we get 1 minus 1, 0. Then we plug in 1, so we get 1 plus 1, which is 2. Then we plug in 1 over here, so it's 2 minus 1, which is 1. And then we plug in 1 over here, so it's going to be cosine of pi, which is -1 times 1. So it's -1 over here, -1. All right. And so we have so what do we have? We plug in 1 here, so we're going to get 1 plus 1 plug in the wrong thing. First we plug in 2, so we're going to get 4 plus 1 plus 1 raised to the 1/2 minus 1 over 1 plus 1 raised to the 1/2. So we get 1 over the square root of 6 minus the square root of 2. So that's relatively easy to find work done just by using this fancy theorem. All right, probably a good place to stop this lecture, and I'll see you in the next one.